Good morning, D-Wolf. Chemistry students, it's me, Mr. Cheney, with another brilliant video. This one is a closed note presentation for the periodic trends right here on Google Classroom. So as you're taking notes, I'm just going to be going verbally through it so that you can hear the information while going through the slide deck and taking your notes at the same time. So here we go. Open up this Gamma presentation here and I will get started. I'll pass out the paper notes as usual, and this is what we'll be taking notes on. So here we go. The chemistry of cooking, how elements behave like ingredients. Never wonder why salt dissolves in water but oil doesn't, or why some ingredients react differently when you mix them. The secret lies in periodic trends, the hidden patterns that control how elements behave. Get ready to discover how the periodic table is basically a recipe book for understanding the chemistry happening in your kitchen every single day. What you'll learn today: learning objectives are explain how atomic radius changes across periods and down groups, predict ion sizes based on electron loss or gain, understand ionization energy and electron affinity patterns, connect periodic trends to real-world food chemistry. Our key vocabulary is atomic radius, ionization energy, electron affinity, cation, and anion. So our criteria for success today: by the end of the presentation, you'll be able to read the periodic table like a menu, predict how elements will behave based on their position, and explain the chemistry behind everyday cooking processes using periodic trends. Alright, so what are periodic trends? The recipe for understanding elements. Think about how different ingredients behave in your kitchen. Flour thickens, baking soda makes things rise, and salt enhances flavor. Just like ingredients have predictable behaviors, elements follow patterns too. These patterns are called periodic trends, and they're the secret code to understanding chemistry. So you have atomic size, how big or small atoms are, like comparing a cherry tomato to a grapefruit. You have ionization energy, and ionization energy is how much energy it takes to pull electrons away. It's sort of like cracking eggs. And then lastly, electron affinity. So how badly do atoms want more electrons? Think of it as like atomic hunger. So here's the cool part. These trends explain why certain foods preserve better with specific salts, why some minerals dissolve instantly while others take forever, and even why your body absorbs nutrients the way it does. Understanding these patterns is like having a cheat sheet for predicting chemical behavior. So atomic radius. Size matters. Measuring atoms like measuring produce. Atomic radius is simply how big an atom is, the distance from its nucleus to its outermost electrons. But here's where it gets interesting. Not all atoms are created equal in size, and the size difference affects everything from how fast ingredients dissolve to how they interact with each other. Fine salt. Tiny crystals dissolve almost instantly because they have more surface area. Small atom atomic size equals faster reactions. Sea salt. Medium-sized grains take a bit longer to dissolve. The size matters when it comes to cooking time. And then you have rock salt, big chunky crystals that take forever to dissolve. Great for slow processes like brining or making ice cream. In the periodic table, atomic radius follows a predictable pattern. Atoms get smaller as you move left to right across the period, and they get larger as you move down a group. This gradient is like organizing your pantry from smallest to largest item. There's a method to the madness. So why atoms change size? 2 rules of atomic size. Rule number 1, more protons equals stronger pull equals smaller atom. So as you move across the period, left to right, atoms gain more protons in their nucleus. More protons means a stronger positive charge pulling electrons closer, like a more powerful magnet. This makes the atom shrink even though it's gaining electrons. Rule number 2, more layers equals bigger atom. As you move down a group, top to bottom, atoms add entire new electron shells, like adding layers to a cake. Each new layer pushes the outer electrons further from the nucleus, making the atom bigger overall. So that's what we went over with the Bohr model, with the different energy levels, 1, 2, 3, moving from the center on up. Then you got sodium and salt. Sorry, over with rule number 1. The sample is sodium and salt. Sodium has 3 electron shells and is relatively small. It has 11 protons pulling those electrons in tight. This small size helps sodium form incredibly strong bonds with chlorine in table salt, which is NaCl, sodium chloride. And then you've got potassium and salt substitute. Potassium has 4 electron shells, making it noticeably larger than sodium. Both are used in salts, but potassium chloride, KCl, behaves slightly differently in cooking because of this size difference. That's why salt substitutes don't taste exactly the same. So then you've got ion size, when atoms gain or lose electrons, the shrinking and swelling of atoms. When atoms become ions, something dramatic happens. They change size. This transformation is crucial for understanding how salt crystals form, how minerals dissolve in water, and why certain nutrients are absorbed in your body. Let's break down what happens when atoms lose or gain electrons. Cations is lost electrons. When an atom loses electrons, it becomes a cation, positively charged ion. Think of it like letting air out of a balloon. The atom actually shrinks. This happens because losing electrons often means losing an entire outer shell. Example, a sodium atom loses 1 electron to become Na+ in table salt. It goes from being pretty big to quite small, about 95% smaller. This size changes why sodium ions fit so perfectly between chloride ions in salt crystals. Then you've got anions, which is gained electrons. So when an atom gains electrons, it becomes an anion, a negatively charged ion. Picture bread dough rising. The atom swells up. Extra electrons create more electron-electron repulsion, pushing the electron cloud outward. So the example is a chlorine atom gains 1 electron to become a Cl- in table salt. It gets significantly bigger, almost twice its original size. This expansion helps chloride ions surround sodium atoms perfectly, creating those beautiful cubic salt crystals you see under a microscope. So this size change isn't just chemistry trivia, it's why salt crystals form the way they do, why some minerals dissolve easily while others don't, and why your body can transport ions across cell membranes. The geometry of these ions fitting together is like chemistry versions of Tetris. Ionization energy. How hard is it to break apart an atom? Ionization energy is the amount of energy needed to remove an electron from an atom. Think of it like cracking an egg. Sometimes the shell breaks easily with a gentle tap. Other times you need to whack it hard against the counter. Some atoms hold onto their electrons loosely while others grip them tightly. Number 1. Increases across periods, left to right. As you move right across the periodic table, ionization energy increases. Atoms have more protons pulling electrons closer, making them harder to remove. It's like trying to pull a magnet off a fridge. The stronger the magnet, the harder it is to remove. Number 2, decreases down groups, so top to bottom. As you move down the periodic table, ionization energy decreases. Outer electrons are further from the nucleus and easier to remove. It's like removing a book from the top of a very tall stack. It's not held very tightly. So the food science application for this is calcium. Calcium has relatively low ionization energy, meaning it easily gives up electrons to form Ca2+ ions. This is why calcium readily forms ionic compounds in milk, cheese, and your bones. When milk spoils, calcium ions interact with proteins to create clumps. That's curdling in action. So other minerals with low ionization energy, like sodium and potassium, also play crucial roles in food. They ionize easily in water, which is why they're so effective as electrolytes and why they conduct electricity in solution. Pretty neat, right? So successive ionization energies, taking away electrons one at a time. So what happens when you try to remove multiple electrons from the same atom? Each electron gets progressively harder to remove, and there's usually one point where the energy requirement jumps dramatically. This pattern explains why some elements form +1 ions while others form +2 or +3 ions. First electron, pretty easy. Removing the first electron is like peeling a ripe banana. It comes off relatively easy. This is the first ionization energy. The outermost electron is the furthest from the nucleus and least tightly held. Remember, that's because the protons are positive and the electrons are negative. So the second electron it's getting harder at that point. The second electron requires more energy because now you're working with the positively charged ion that's holding its remaining electrons tighter. It's like trying to peel a slightly underripe banana. It's doable, but it takes a little more effort. And then lastly, you got your third electron. That's the big jump. Often there's a massive jump in energy needed. This happens when you're trying to remove an electron from a stable, filled inner shell. It's like trying to peel a banana that's already been peeled. Nearly impossible and definitely not worth the effort. So here's just kind of a graph that shows you the jump as far as being able to do that. So notice the huge jump from second to third electron. This pattern tells us why sodium typically forms Na+, not Na2+, and why magnesium forms Mg2+ and not Mg3+. Atoms will lose electrons until they reach a stable configuration, but they won't expend crazy amounts of energy to break into energy shells. It's all about finding that sweet spot of stability. Alright, so electron affinity. Electron affinity measures how much an atom wants to gain in electrons, basically how hungry the atom is for more electrons. Some atoms desperately want electrons, releasing energy when they get them, while others couldn't care less. This hunger determines how reactive elements are and which compounds they'll form. So high electron affinity, they really want electrons. So elements on the right side of the periodic table, especially halogens like chlorine, fluorine, and bromine, have high electron affinity. They're like someone who's been fasting all day. They'll grab that electron eagerly. When these atoms gain electrons, they release energy because they're reaching a more stable state. Low electron affinity, they don't really want electrons, and those are elements on the left side, and noble gases have low or negative electron affinity. They're like someone who just finished a huge meal. They don't want any more. These atoms either don't accept extra electrons easily or require energy input to take them. Food preservation connection to this. So chlorine has one of the biggest electron affinities of all the elements. It desperately wants that extra electron to complete its outer shell. This extreme reactivity is exactly why chlorine compounds are used in food preservation and water treatment. Chlorine's hunger for electrons makes it an excellent sanitizer that destroys bacteria by disrupting their cellular chemistry. When chlorine gets that electron it craves, it becomes the chloride ion, Cl-, found in table salt. Much more stable, much less reactive, and perfectly safe to eat. Okay, common ion charges, the usual suspects in your food. Now that you understand the trends, let's meet the ions that show up constantly in your food. The pattern is beautiful. It's an element's position on the periodic table actually predicts what charge its ion will have. This is periodic trends in action, making chemistry predictable and useful. So sodium Na+, charge, the charge is 1+. That's found in table salt, preservatives, baking soda, and practically every processed food. Sodium loses 1 electron easily, low ionization energy, to achieve stability. Calcium, Ca2+, is a +2 charge. That's essential for milk, cheese, fortified foods, and strong bones. Calcium loses 2 electrons because it's in group 2 of the periodic table. Do you see the pattern? Potassium, K+, is a 1+ charge. That's abundant in bananas, potatoes, and salt substitutes. Like sodium, it's in group 1 and loses 1 electron to form stable ions. Chloride, Cl- is a charge the other half of table salt. Chlorine gains 1 electron, high electron affinity, to complete its outer shell, found in salt, pickles, and brines. And then you have iodide-, which is a -1 charge, added to iodized salt to prevent thyroid problems. Like chlorine, iodine is a halogen that gains 1 electron, essential for your metabolism. So the pattern: group 1 metals form 1+ ions, group 2 metals form 2+ ions, group 17 nonmetals, the halogens, form 1- ions, and the periodic table literally tells you the charge. So once you know this pattern, you can predict ionic charges for tons of elements. Okay, putting it all together. So reading the periodic table like a menu. Everything we've learned, atomic size, ionization energy, and electron affinity, works together to predict chemical behavior. Let's see how those trends combine to explain one of the most common compounds on Earth. Good old table salt, NaCl, sodium chloride. So atomic size trends. Decreases left or right, increases top to bottom, small atoms form stronger bonds. Then you have ionization energy, increases left to right, decreases top to bottom, metals have low values. And then you have electron affinity, increases left to right, nonmetals desperately want electrons. So why sodium chloride forms so easily? Sodium's low ionization energy, it easily loses its 1 outer electron to become Na+, that's the sodium part, the metal. Chlorine's high electron affinity, so it desperately wants that electron to become Cl-, because chlorine on the right side of the periodic table has 7 electrons in its valence outer shell, and that 1 more will make it stable. Remember, 8 is a complete shell. So both are small. Na+ is tiny after losing an electron. Cl- is compact, so small ions equal strong electrostatic attraction. And so the perfect size match. They fit together beautifully in a crystal lattice. So the result is perfect table salt. The combination of sodium's eagerness to give up an electron and chlorine's desperation to take one creates an incredibly stable compound. The energy released when they bond is substantial, making NaCl very hard to break apart. There's a high melting point of 801 degrees Celsius. This stability is why salt has been used for thousands of years as a preservative. It doesn't decompose easily, it doesn't react with most foods, and it's safe to eat. Periodic trends explain it all. So, practice and review. You're the chef now. Time to test your understanding. Use what you've learned about periodic trends to answer these questions. Think through the patterns, atomic size, ionization energy, electron affinity, and ion charges. So, predict magnesium versus calcium. Which element would be easier to ionize? Has low ionization energy? Magnesium or calcium? Remember, ionization energy decreases as you go down a group, so top to bottom. So is magnesium on top or calcium on top? So if you go to the periodic table, you're going to see that calcium, it's lower on the periodic table, so outer electrons are further from the nucleus. So explaining salt substitute chemistry. Why is potassium chloride used as a salt substitute for sodium chloride? NaCl. Think about their positions on the periodic table and their chemical similarities. Both are group 1 elements with similar properties. They both form 1+ ions and bond with chloride the same way. So group 1 at the very far left. And then design your own ionic compound. So choose one metal from groups 1 or 2 and one non-metal from group 17. Predict the formula of the ionic compound they'll form. Use periodic trends to justify your answer. So an example would be magnesium plus bromine, which would be MgBr2. Mg forms 2+ ions. Br forms 1 negative ion, so you need 2 bromides to balance it. So understanding periodic trends isn't just memorization, it's learning to see the patterns. Once you see them, chemistry starts making sense instead of feeling random. Okay, so the real-world applications of all this. Beyond the kitchen. Periodic trends aren't just abstract concepts. They're working behind the scenes in countless real-world applications. From the food you eat to the water you drink, these patterns shape the chemistry of everyday life. Let's explore where periodic trends show up outside the classroom. So, food preservation. Salts, acids, and other ionic compounds preserve food by controlling water activity and creating hostile environments for bacteria. The small size of Na+ and Cl- ions lets them penetrate food effectively, while their stability ensures long-term preservation. Nutritional supplements. Minerals and supplements come in ionic forms because that's how your body absorbs them. Calcium, citrate, magnesium oxide, iron sulfate, all use periodic trends to maximize bioavailability. Low ionization energy metals become the ions your cells need. And then water treatment. Ion exchange systems remove harmful ions from drinking water by swapping them with safer ones. Understanding electron affinity and ion size helps engineers design filters that selectively remove lead, mercury, and other contaminants while keeping beneficial minerals. So future careers using this knowledge: food chemist, nutritionist, food safety specialist, flavor chemist. And then here's just a summary of the periodic trends that we covered. You can now understand to read the periodic table like a pro. You've learned that atomic size, ionization energy, and electron affinity aren't just random numbers. They're predictable patterns that explain everything from why salt dissolves to how your body absorbs nutrients. So there are 3 major periodic trends: atomic radius, ionization energy, and electron affinity. 100% predictable patterns. The periodic table tells you exactly how elements will behave. And then the real-world applications, from cooking to medicine to engineering, it's everywhere. So your key takeaway: chemistry isn't about memorizing facts, it's about understanding patterns. The periodic table is your roadmap to predicting how elements behave. Now you know how to read it. Next time you're in the kitchen, remember, you're not just cooking, you're doing chemistry.